Um, Welcome to Information Theory. This is lecture 15. I guess before we begin, I just want to say a couple of words. I don't know if any of you know who Ben Taskar is, but he was a friend of mine. He was a professor in the machine learning group in the computer science department here at UW. A lot of what we do in information theory relates to machine learning, I think. And some of what I am teaching is sort of from that perspective. And Ben was he died suddenly, had a sudden heart attack at age 36 on Sunday evening. And it's, as you know, not just a friend of mine, but he also, his wife and his daughter and his family and everything. It's a very sudden thing. So I just want to mention him and just take a moment to sort of, honor his memory and to I mean, you unfortunately, as students here, won't have the opportunity to take a class from him in the future. He was a really extraordinarily nice person, and he had just an extraordinary soothing quality about him. And at the same time, he was extraordinarily gifted technically. He was technically great, but sort of personally soothing, and it's sort of a very rare combination of person. So. I'd like to at least dedicate this lecture to him and his family. So, with that said, let's get started. So this is lecture 15 of information theory. I have to apologize because I know that I've said that the homeworks we're going to be due on Thursday nights, and I haven't yet produced a new homework yet. Obviously, I'm not going to, if I produce a homework today or this afternoon, it won't be due Thursday, or if it is due Thursday, it will be very Short. Because I'd like to try to have things due on Thursdays again. So if you see homework tonight, it will probably be just a couple of problems. And then the more longer homework will be due next Thursday. And I know next Thursday is Thanksgiving, but thanks to the electronic way that we are doing assignments, there doesn't seem to be any reason to have assignments due during class any longer. But I don't know. So maybe it'll be due Friday or something. But we only have a couple more weeks of class. I mean, so we have this week, and then we have next week, which is a half a week, and then we have the following week, and the following Tuesday we have a final exam. So we're getting into the final stretch of the material. Anyway, that's that. So do be on the lookout for a homework that will most likely be due on Thursday, but it will be a short one. And we're still covering Chapter 7 material. In fact, we sort of left the lecture last Thursday halfway in the middle of a very important proof, which was also, unfortunately, a very non-ideal place to stop. And so as a result, I'm going to have to go through, and I think it's only makes sense to go through a little bit more review this time, maybe quickly review the beginning part of the proof today. So yeah, this is on the homework. So homework 6 will be out soon. Just a reminder to everybody that our office hours are now Thursdays. People haven't been taking enormous advantage of office hours, and I've only so far had one Canvas conference session customer. And I can attribute that to one of three possible things. Actually, so the three possible things are either my lectures are so easy to understand that nobody has any questions, and I find that hard to believe. The other possible thing is that Canvas is a terrible software system and nobody wants to try it. Or the third possible thing is that maybe it's not at a convenient time, or some combination of the above. So I do want to stress again that if my goal is to have everybody really learn this material, and I can only succeed in that endeavor to the extent that you want to learn. And wanting to learn means that you might have questions, or you might want to come to office hours, or just email questions and those sorts of things. So if there's anything that's unclear, and you obviously also have a goal in taking this class. I mean, you want to learn about information theory because you think it's interesting or useful or cool or all of the above. So please do then take advantage of these times that I'm offering. Or, as I've said a couple of times, if you can't make it, then we can set up a separate conference or meeting, and it doesn't have to be in person. I can do Skype in the evenings or something. So feel free to contact me. So, okay, so what I'm going to do here, so this is the point of last lecture that we stopped. And what I'm going to do is I'm actually going to jump back to lecture 14 to this point, which is exactly where we stopped. And I'm going to just briefly review this, actually. Hold on a second. Oh, this is the same problem. Okay, 1 second. Okay, so now we're live again and we're doing a review. On YouTube, you won't experience any of the delays that we just experienced live. So just to recall, we're saying that a channel is symmetric if if there are certain properties of the transition matrix that are true, namely that rows and columns are permutations of each other, and the channel is weakly symmetric if the rows are permutations of each other, which basically means that the row entropies are the same, and as a result of the row entropies being the same, we can express the channel capacity of any symmetric channel. It doesn't have to be a binary symmetric channel. So a binary symmetric channel means that the cardinality of y and x is 2. Of course, it's a binary. This is an n-ary symmetric channel. And saying that the entropy is, or the capacity is given by log of the maximum entropy of y minus the entropy of all of the rows. Okay, so that's an important, very simple channel that we study. Now we have a number of different properties of channel capacity. That it's because it's based on an optimization of the mutual formation. It's going to be, of course, greater than 0, and it's bounded above by the maximum entropies of either x or y. And it's a continuous function of p of x. And in fact, it's concave for p of x when we fix p of y given x. And that's important. That will be particularly important next quarter when we do rate distortion theory. And also, what's also going to be important is that it's convex as a function of the capacity for a fixed p of x. That will also come up next quarter. We're not going to use that really this quarter. So the idea, we get this intuition of bin packing, where we basically choose a code. This is the intuition of Sandin's second theorem, is that we choose a code word for a given message. And when we send that code word, it can get distorted. And there's sort of a region in the receiver space of received code words that could possibly correspond to a given sent code word. And as long as these regions, these small white circles, don't overlap, or as long as the overlap can be made as small as we want, what we can do is then choicely select a subset of the possible code words we could send. So these black dots on the left correspond to a subset of the possible code words. And then if we only send one of those code words, then we know on the receiver end that we're going to get is something, anything within one of those white circles. And as long as the white circles don't overlap, we can map anything from within that white circle back to the corresponding code word. And so what this does is it's like a bin packing thing. It's like, okay, well, how many white circles can we fit into the big yellow oval? And we want to pack as many as possible in there. And then find a code word that corresponds to that noise profile, the profile of the white circles. And then it becomes a bin packing argument, and we get this thing here where the numerator is the 2 to the nh, which in some sense is like the volume of the yellow oval. It's like the total number of possible typical y's that we're going to see. Because when the block length gets big, that's as many possible, that's it, like it's 2 to the n y. We're not going to see anything that's non-y typical. And then the denominator is, okay, what's the typical y given x region? And that's 2 to the n y given x, 2 to the n h of y given x. And so it's the big volume divided by the small volume, and that gives us the total volume, which corresponds to the number of messages we can send. And so that's 2 to the n I, which is I is the mutual information. And then if we maximize that, that's sort of finding the right p of x to maximize that, and that gives us the capacity. And that's the intuition. What we need to do is prove that. So we have a definition, which is what is an MN code. An MN code is it's really meant to sort of correspond to a sequence of codes, because we can talk about a sequence of MN codes. But for a particular m and n, we've got a channel which corresponds to an x symbol set, or a p of y given an x symbol set, and a y symbol set, an index, which are 1 through n, those are the messages we want to send, an encoding function, x of n. It's very strange not to be pointing at this when I'm talking about it. I could be pointing at the screen. And then a decoding function, g. And so g basically takes a received sequence of channel output symbols and maps it back to a message. And of course, if we apply g to y, to the output of the encoding of a message, and we check whether or not the sent message and the received messages are the same or not, and that gives us a way of measuring the error, and we want to essentially come up with a probability of error. And we have a lot of these different methods to measure the error. We have the message, the probability of error for a particular source message being sent, which is lambda I for source message I being sent. There's a maximum probability of error for maximizing overall I. And there's also an average probability, which is just averaging overall I. And what we're going to show is a really cool trick, which is that when the average error is small, we can show that the maximum error is small. How can we do that? That's sort of the critical insight that he showed, which we're going to see. We haven't done it. We didn't get to it last time. Okay. Rate. Everybody should be familiar with the concept of rate at this point. It's the number of bits needed to specify one of m messages divided by the number of channels that we use. And so it's in units of bits per channel use. And we have the notion of achievability. So remember, we have the information capacity, which is the result of this optimization over p of x of the initial information function. And we have the notion of achievability. Can a given rate be achieved? And achievability means there exists a sequence of codes at that rate that has vanishingly small probability of error as the block length goes up. And the block length is the number of channels, number of times we get to use the channel. So in general, just like in source compression, in source compression, we need to block encode. So rather than coming up with a bit string for each individual source symbol, we come up with a bit string for a sequence of source symbols, even in the case when they're independent. And that's the only way we can get close to the entropy rate in source coding. Channel coding is the dual, basically. The only way we can get close to the capacity of the channel is by block coding. So we have one of m messages, but we're going to be, for each one of those messages, we're going to be needing to use the channel multiple times, sending a few bits each time. But overall, the rate is basically the total number of bits we send divided by the number of times we use the channel. There's the capacity of a discrete memoryless channel, which is the largest achievable rate. And what we want to do is connect the capacity to the information theoretic, the information capacity, which was this guy right here. There's the notion of joint typicality. And this was kind of the same as before. So we have x typicality, so it's the marginal typicality for x, y typicality, and then the new thing is this bit here, where we have joint x and y typicality. So we need to be both x typical, y typical, and xy typical to be jointly typical. That's the definition. And we have the joint asymptotic equipetition property, which basically says, so let this sequence xn, yn, so it's a sort of a vector sequence, length 2 vector sequence. I mean, length is n and its elements of size 2. And it's drawn from this distribution. And this is not an independent distribution. It's independent over uses, but x and y are not independent. Right? So in general, x and yn are not drawn independently because there's dependence between the corresponding xi's and the yi's. But there's not dependence between xi and yj for I not equal to j. So that needs to be clear. So under that distribution, the probability of the typical set goes to 1 when n gets big. We have an upper bound on the size of the typical set and a lower bound, which is exactly analogous to what we saw in chapter 3. Point 3, which there were a couple of questions about last time, was if we were to draw x and y independently, meaning x and y are independent, meaning xi is independent of yi for all I. If we were to take two independent sets, then the probability of that being typical, there's some possibility, but it's a very small probability, and basically it's equal to 2 to the negative n mutual information. And so as the mutual information increases, that probability gets very small. If x and y truly are independent, then the bound is somewhat meaningless because it's just 2 to the 0, which means it's less than or equal to 1. Right? And moreover, we have a lower bound, which basically says that when n is very large, we also have a lower bound on the probability. Okay. Right. And this property 3 is going to be critical, because this stuff here, property 3, is going to be what allows us to bound the probability of error once we define what kind of error we have. So, so the theorem says that all rates below the capacity, the information capacity, are achievable, which basically means that as long as the rate's not greater than this information theoretic capacity, then that rate is achievable, meaning there exists a sequence of code such that the probability of error goes to 0 as n gets big. And secondly, the converse, which we haven't started yet, is that if it's the case that the probability of error goes to 0, it must be that the rate's less than capacity. So capacity, again, is this critical point. Okay, any questions on the review? Actually, there's more review because we're gonna briefly cover the theorem again, or the first part of the theorem. Are there any questions on the review? Everything fairly clear? This is your opportunity. Okay. You can formalize questions, because now what I'm actually going to do is pause. Okay, so as we discussed last time, all code words get their choice being assigned to every possible message that we want to send, or that we might want to send. So when we take the average over all code books, we're essentially placing, in turn, every possible code word for each message, for each W that we want to send. And so one way of looking at it is this picture over here, where we have omega, which under one code book might be assigned to this code word x1, on another code book might be assigned to this code word x2, and for another code book, and so on and so forth. So these are, like, for example, 4 different possible code words that might be assigned to the message W. But each one of them has, in some sense, the same probability of error, because, you know, every such, the probability of error depends on the dispersion. You know, how does x1 disperse over to y1 to y4? And so when we average over all of these things, regardless of what W is, every W is going to essentially have a turn using each one of these 4 code words. And so therefore, it doesn't matter what W is. The W essentially cancels out in some sense, or it doesn't matter, averages out. So the error is basically probability of choosing x1 for W and not choosing y1 plus the probability of choosing x2 for W. But the probability of choosing each one of these code words for each of the W's is the same, because the code words, or the code books, are generated randomly. Right. So we can pick any message. And so now so that's what we get in equation 15.2. This stuff is just basically the sum. We've got this very, very large exponential sum over beta, but it just turns into beta. Okay, so beta is basically the probability of error given that the message that we want to send is equal to 1. Okay, so now what we're going to do is define a bunch of random events. And the random events are going to indicate our errors, the possible errors. So E sub I is basically equal to the following. It's the event that the pair, the code word corresponding to message I, and what we received Y is jointly typical. Okay, and remember, we're sending W1. So because we're sending omega is equal to 1, we're assuming that the first code word was sent. Okay, so that means no error means the following. No error means that, okay, this guy with I is equal to 1 is jointly typical with what we received, and not any of the other possible code words are jointly typical. Okay. So we've got joint typicality of 1 exclusively. Right? That excludes all possibilities. It excludes the possibility of none of them being jointly typical, because E1 being true means that the code word corresponding to W omega is equal to 1 is jointly typical. And it also excludes the possibility of there being more than 1, because the only way there would be more than 1 is for EI to be true for more than one I. But again, because we can only send, because we're sending omega is equal to 1, we can get by with just dealing with that. So the complement of E1 means that the transmitted, so X of 1 is the transmitted code word. The complement of E1 means that the transmitted code word is not jointly typical. This is type error B. And then the union of all these other guys, this is another possible error. This is either that the wrong code word is jointly typical, for example, like maybe, which could mean that there's more than one, or it could mean, it could mean that the wrong one is jointly typical, which could possibly happen if E1 is false. Or if any of these guys are true, it means that there are two of them that are jointly typical, and that was something that we said we were going to consider an error, because when there's two of them or more, we don't know what the sent code word is, and so we don't. In that case, we're just going to have an error. And what we want to do is bound the probability of the error. So we've got errors A, B, and C from before covered. And bound the probability of error. So here's a picture that sort of shows what's going on. I think I've got another picture here. So remember, we have the sort of marginally typical X sequences here, the marginally typical Y sequences here. Along this diagonal is kind of a cartoon figure of the jointly typical sequences. And here we have the idea of 4 code words being chosen, X1, X2, and X3, and X4. And these are the jointly typical, these are the things that X is jointly typical with Y. And so here's sort of a nice picture that sort of explains everything. So the first one is, let's say that you send X star, which basically means you send any source, any code word for anything. So let's say you send X star, and you find that, you send this thing, and you find that it's jointly typical with this dot here. And you see that, oh, it's not jointly typical with any of the thing that I receive is not jointly typical with any of the code words. And if the thing that that's basically then E1 complement. Because when we look at the received Y and we find what it's jointly typical with, sure, it's jointly typical with some X, some string of X. But none of those X's happened to not be assigned to any code word, and so therefore that's an error. Another error is basically, suppose we send X1, and what we receive is something that's jointly typical with X4. That's wrong, right? So it's jointly typical with the wrong thing. Here, here we've sent X4, say, and it's jointly typical with X4. That's correct. That means that this case here is good. And this last case is basically assuming that we've sent X1, the code word X1, and it's jointly typical both with X1 and X3. Okay. So in those cases, it has to be an error. There's more than one. So we want to bound all these types of errors. So the probability of the error given omega, so given W is equal to 1, is equal to the probability of the union of these events, which by the union and bound, again, we can separate out. And we can upper bound it, and we want to, and this is sufficient. This is actually, the union bound is a pretty bad bound, but it's good enough for us, because if we can show that each one of those things decreases exponentially, we're in great shape. So the first guy, the probability of the complement of E1, well, that we already know from the asymptotic equipartition property is epsilon. That can be made as small as we want. That goes to 0. So that's the probability of the atypical set. In other words, that means that there's some n naught such that whenever n is big enough, we can make this as, we can make it smaller than epsilon, that probability. Now, the other thing is that this is a random code generating process. Right? So every code word is independent of every other code word. When we're thinking about this as random variables. And so therefore, when we receive a Y, and it happens to be jointly typical with something which is not the code word that we sent, we can bind the probability of that because those are going to be two independent events. Since the Y is only going to be dependent on the code word corresponding to the message that was sent. But if there's some other code word that it happens to be jointly typical with, we can use that probability of independence, being two independent XYs being jointly typical. And it ends up being that case. And the reason why is because since X1 is independent of Xi, for all I not equal to 1, that means that the received sequence is going to be independent of xi for all I not equal to 1. And so therefore, we use that probability. We use this thing. These guys are independent events. Again, with I not equal to 1, these are independent events. And so therefore, this is upper bounded by 2 to the negative mutual information, minus some epsilon stuff. So that's going to be useful for binding the other errors. So as long as the question.
Y1 is independent of x2, x3. I'm just trying to relate it to the BEC, for example.
Great, so,
why can't we say it in the BEC and we can see it?
Okay, well, the first question I understood, and so the first question is why is it independent? Because think about the code generation process, right? So the code words are really a random variable. Right? I mean, to talk about independence, you have to say, okay, there's randomness somewhere. There's talking about a random variable. Think about the whole process as a random process, the whole decoding process, which is governed by this distribution P of script C. Right? So we can talk about now, like if you want to think about it as capital letters. So all of the code words are capital letters, and they're all drawn independently and identically according to P of X. So that means that every code word, in fact, every code symbol is independent of every other code symbol.
Yeah, that's good. But how about the channel?
Well, right. So the channel, if we send the ith code word and receive y, so y is going to be not independent of the ith code word. But it is going to be independent of another code word because we didn't send that code word. So remember, we're only sending message number 1, right? So we're sending message number 1, meaning we're sending the ith code word, or sorry, the first code word corresponding to 1. So think of it now as a random variable. We've got a bunch of random variables corresponding to the first code word, and you've got a bunch of random variables corresponding to the received sequence. Those two guys are going to be dependent on, not independent.
Given x1 or 7.
Yeah, we're always assuming x1. Remember, this is all given that w is equal to 1. Remember, that's the key assumption. So you're right. We have to make this, but that we've already handled that situation. We've said we can just condition on w is equal to 1. But it doesn't really matter. I mean, you could take any message. It doesn't have to be 1. It could be 37 or 422. As long as it's fixed, because they're all identical. And so let's just use 1 since that's the easiest to remember. Or you could use 2. 3 is okay. When you get to 7, it gets a little hard to remember. But 1 is pretty good. So therefore we've got that the only thing that y could possibly be dependent on is the first code word, not the others. And so if it happens to be the case, like E2, E3, and so on and so forth, that basically says that y is jointly typical with any of these other guys. That's basically the case when independent xy's are jointly typical, and that's for the thing we exactly have a bound for, based on AAP. Very good question. I love getting questions, as you can tell. Does that answer your question? Does it make sense? Okay, good. I like it also when people benefit from my questions. Okay, so that we got the probability of error. This is the union bound according to 15.10 on the right-hand side. So the probability of the complement is just epsilon. This is just the complement of the typical set. And now each one of these guys, the union bound has done us a favor. It's broken these into individual events. It's just the probability of EI. But each one of those corresponds to these independent xy's being jointly typical. And we have a bound for that as well, an upper bound, which is to the negative n mutual information, which is this thing. So this is the upper bound of this. And we're just summing over all I. Okay, so now we can just count, since they're all the same, and we've got 2 to the nr minus 1 as a count. And let's put that up in the exponent. So it's just it's doing a little bit of algebra to put this in the exponent. We've got 2 to the 3n epsilon times 2 to the negative n I minus r. Now this should start looking very, very promising, because now we've got something, mutual information minus the rate. And you know that the mutual information is going to be maximized, and if the rate's going to be smaller than the capacity, then we want something to die to 0. So let's see how that works. So that basically corresponds to this. It's the mutual information minus 3 epsilon minus r. So it's basically close to the mutual information minus r. And that, as long as the mutual information is greater than 3 epsilon, that's going to be less than 2 epsilon. And the reason is because we're assuming in this case that the rate is less than the capacity, or rate is less than mutual information. So this is true as long as this is true. Right? Because we need this quantity here to be positive in the exponent. So therefore, if we choose r less than the mutual information strictly, we can make epsilon as small as we want so that the 3 multiplied by epsilon doesn't matter. And then we can make the average probability as small as we want, 2 epsilon. Okay, everybody see that? Now, this is the next critical trick. The average probability of error isn't enough. The average probability doesn't mean that the maximum probability is bounded. And what we want to do is bound the maximum probability, meaning that there's some code that gets it. So first thing we do is we choose the maximizing source probability so that we can change the mutual information to C. Right? That doesn't matter. We haven't really made any required assumptions. None of this is we've actually used the uniform distribution, which is the highest entropy P of x. And so now we're going to maximize the mutual information. And then what this says, so if we do have that the probability of the error is less than or equal to 2 epsilon, you know, if the average is upper bounded by something, there has to be at least one code whose probability of error is less than 2 epsilon, right? Has to be one of them. Otherwise, if they're all greater, if all of their errors are greater than 2 epsilon, the average is not going to be less than 2 epsilon, less than or equal to 2 epsilon, right? So let's just choose that one. Choose whatever it is. So again, there might be a lot of them. You know, there's a super exponential number of them, but let's just pick whatever that is. And so assume that C star is one of those guys that has bounded probability of error. And just to remember, this is the bounded average error. So this guy who's got bounded error is represented this way. So this is the error under C star. This is the error of sending the ith code word, or sorry, sending the ith code word, averaged over all to the nr possible code words. And we can break this up into 2 mutually exclusive sums. These are the i's for which this probability of error is less than 4 epsilon, and this is the i's for which lambda I is greater than or equal to 4 epsilon. Okay, just partitioning the terms in the sum. Got it?
And then we have epsilon, 2 epsilon, 3 epsilon, 4 epsilon.
I can guarantee you we won't have 5 epsilon. But yeah, we have 2 epsilon. But it could be much worse, actually. But just look at it locally. I mean, going from equation 15.17 to 15.18, it's just partitioning the terms in the sum. Okay? The ones that are less than 4 epsilon, the ones that are greater. The average is going to be, we know that the average is going to be less than 2 epsilon. Because the average over all codes was less than 2 epsilon, which we proved from before. Okay, so the average is less than 2 epsilon. We've broken up into 2 terms, two blocks. Now, what we're going to show is that we're going to show that this sum can't be too many. So in other words, we're going to show that this has to be less than half. So the reason why is the following. Suppose that more than half of the indices, so like there's 2 to the nr terms. Suppose that more than half of the terms had error greater than 4 epsilon. So in other words, this guy summed over greater than 2 to the nr over 2, which would mean that this guy is less than 2 to the nr over 2. Okay, under that assumption, if this guy has more than half of the terms in the sum, of the total number of terms, which is 2 to the nr, then we can say, okay, well, here's the right-hand side. This bit right here is just this, right? We're just taking the right-hand side. Well, each one of these lambda i's is greater than or equal to 4 epsilon. So let's just plug in 4 epsilon here. For right here. But now we can pull out the 4 epsilon and just do counting. But we know that this thing, this counting thing, we're under that assumption is this is greater than or equal to 2 to the nr over 2. And as soon as we put that in, this cancels out here, this term, and we've got an additional 1/2, which turns into 2 epsilon. So basically what that means is that this whole right-hand side becomes already strictly greater than 2 epsilon. So if this right-hand side is strictly greater than 2 epsilon, it can't be less than or equal to 2 epsilon. So therefore, the assumption that more than half of the terms have error greater than 4 epsilon must be false, which means, therefore, that more than half of the terms have error less than 4 epsilon. Okay? And that's a little tricky. If that doesn't make sense, maybe try to go through it again. But it's really cool. This was like the critical insight. So there can't be, so these alone would be more than 2 epsilon. I've already said this. So therefore, the assumption, otherwise, it doesn't lead. So more than half, at most half of the code words have epsilon greater than 4 epsilon. And this means that the number of terms that have error less than 4 epsilon, strictly less than 4 epsilon, is at least to the nr of 2. So now what we're going to do is we're going to create a new code book. We're going to reduce our rate in doing so, but we're going to create a new code book that eliminates all of these bad code words. So we're starting from C star, that one that achieved average error of 2 epsilon. Let's create a new code book that gets rid of all these bad guys, which we could do. And we know that there are at most half of them. We're not getting rid of too many of them. So therefore, we're increasing our rate not so badly. So the remaining code words are of size, the number of code words are 2 to the nr over 2, at least. Right? So we're getting rid of at most half of them, which means that we're only increasing the rate by 1 over n. Decreasing the rate by 1 over n. That's what this does. But that looks really good because it's a function of n now. And as the block length gets big, we can make that as small as we want. And each one of these code words has a maximum probability of 4 epsilon. All of a sudden, if we want to compute the maximum probability of the code book, we know it's going to be 4 epsilon. I mean, not the average, but the maximum. Because remember, we broke it up. So all these guys are the good ones. These are all the ones that have. So we broke the average into 2 parts. The ones that are bad, the ones that are good, and we showed that this includes in the worst case, half of them. So that if we get rid of these, we still have a lot left, and we haven't decreased our rate so much. And the rate, moreover, r prime is r minus 1 over n goes to r as n gets big, but has maximum probability 4 epsilon. So that's basically the end of the proof. It's basically saying, okay, there exists this code. We started by taking this average over all possible code books. We found an error of 2 epsilon, which basically means that there must be one code book that has an error at most 2 epsilon. We take that one code book, we partition the code words into the bad ones and the good ones, take the good ones. We show that we have at least half of the ones that are good ones are these code words. And then that one has not, since we still have a lot of code words, we have not decreased the rate very much, and it has maximum probability. 4 epsilon. And 4 epsilon, again, can be made as small as we want. The 4 doesn't matter. Anytime you have a constant times an epsilon, it doesn't matter. Every time you have these kinds of proofs that talk about 2 epsilon or 5 epsilon or anything, it basically comes from adding a bunch of terms, which are at most epsilon. It just so happens that, where does the 5 come from? Where does the 2? It comes from just that you've broken it down, you've broken the algebra down into some number of terms, each of which has some bound involving epsilon, or upper bounding epsilon. That's what we did here, at least. So what the coding method did is it showed that if the rate is strictly less than the capacity, there exists a sequence of 2nRn codes with maximum probability of error going to 0 as n goes to infinity. So it's not the best code. It's sufficient. It's an existence proof. It doesn't guarantee that, it guarantees the existence. It doesn't give us one. And this started, this theorem started this huge push towards good coding methods and Hamming codes. We're going to talk a little bit about Hamming codes later, Thursday and next Tuesday. But like I said, we could have an entire class on coding theory. I wish we would. It's up to you. If you want to protest outside of the EE admin office saying, we need coding theory classes. You could do that. You could organize. You could boycott. You're being students until you say, we're not going to be a student until we get our coding theory class. I would be happy to teach it, although maybe I would debug this process by then. There are many good practical codes. The other thing is, of course, that the codes have to be practical, because when we want to use these things in our cell phones, they have to be computationally feasible and energy efficient. Turbo codes, Gallagher codes, which I've mentioned before, these are these LDPC codes, low density parity check codes. And every year there are new ones still being proposed. Right. Okay, so we need to prove the converse. We haven't proved the converse yet, the theorem. The converse basically says that if you do have a sequence of codes with vanishing probability of error, vanishing maximum probability of error, that the rate has to be no more than the capacity. But before they do that, let's consider one really easy case to show. Like, suppose we put a really strict thing. Like, in other words, this next statement. Let's assume that the probability of error is exactly 0. Not that it goes to 0, but it's exactly 0. In that case, it turns out to be very easy to show that the rate is upper-bounded by the capacity. We'll do that first. But before we do that, let's take a break, and then we'll try to finish up with this. Okay. Okay, so we're back, and we are actually back with our iPad version again. So I don't know why, but during break it suddenly started working. But in any event, what we're planning to do is we want to show that any sequence of codes that has vanishing probability as a function of the block length that's got rate less than capacity. And we're first going to show that one sufficient condition for vanishing probability is when the error is just flat out 0. And when that's true, we'll have this as a consequence. So if the probability of error is 0, then when we receive a given y, there's no uncertainty about w. So this whole thing is going to be 0. We're going to be able to, the error is 0, which means that we must know with absolute certainty the underlying message that was sent. And what we're going to do for simplicity, and also because it's sufficient, is that we're going to assume that the distribution is uniform over messages, which means that the entropy is NR. Okay? So it's the max rate. So what we're going to do is show that this max rate, or R in this case, when the probability of error is equal to 0, is going to be bounded above by the capacity. And this is actually pretty easy to do. So the way we do this is start with NR, and that's going to be our entropy. And the entropy can be written as the entropy of W given Y plus the mutual information between W and Y. That's just using, what property is that using? It's the definition of mutual information. Right? And that's just equal to this. Now, why is that equal to this? Because this bit here is equal to 0. Right? Oh, this is so much nicer when I can write on it, isn't it? Everyone's back and everyone's happy again. This is upper bounded by this quantity. And the reason why is because remember, this is the Markov chain that we've got. We're starting with the message. We encode it in a set of code words, and we send it over the channel to get Y. So this is a Markov chain, and then when we're looking at this these two quantities, this quantity here corresponds to w and y, and then this has got to be bigger since x and y are closer in the Markov chain. This is the data processing inequality that we learned from chapter 2. And this is equal to this quantity here. And we can write this using the chain rule of entropy. This is the chain rule. Well, the whole thing is the chain rule. But now we're going to use this property of independence, which is basically saying that yi given xi is independent of all of this other stuff here. And so we can continue the above as essentially once we've got xi in this quantity, we can get rid of all of it except for xi here. Because of the independence property. Now we upper bound. So the entropy of y is upper bounded by the entropy of the sums of the marginals, and we get this upper bound. And now we've got this sums of mutual information terms down here. And that lastly is upper bounded by n times the capacity. So now we started with nr less than equal to nc. It's very simple, yeah, very simple. But this is not good enough, right? Because this is assumption of zero error, right? So like I said, this is an instance of, this is a sufficient but not a necessary condition for what we ultimately want to assume, which is that the error goes to zero, not that it is zero. Okay, so now, it's one other caveat about this. So the other thing is that the proof shows that the entropy of W is less than or equal to NC. So the entropy of W is less than or equal to the max. This is true for all distributions. So we take the max, which is N is equal to less C. So we get this regardless of the source distribution. So there's no crime or worry or loss of generality in starting with the uniform distribution. Now there's also a sublemma that we used in that proof, which we are going to use again, which is that this is true. And so let's just give it a name. Let's call this lemma 15.4.1. That's what they used 40 years ago. They used 15.4.1. And I just thought we should keep using that name. So the lemma 15.4.1 is that this mutual information is less than or equal to n times capacity. Now the other thing is, recall back from our chapter 2 days, Fano's inequality. You might have forgotten about Fano's inequality because we didn't really use it for entropy compression. But Fano's inequality says that the conditional entropy of x given y, it's upper bounded by 1 plus the probability of error plus the log of the alphabet size, log of the size of the alphabet size. So that's, I guess, officially a typo here. It's log of the alphabet size, and P of V is the probability, is the error indication of, under, again, this sort of channel when you send X and you receive Y, and the probability of it not being the same. So here's the version of Fano in our context. The probability of error in our context is the probability that the decoded message G, of the received string is not equal to what was sent. So that's our probability of error. And we can just quickly prove that by, it's analogous to the proof of Fano's inequality. We define this error event, which is the probability that what was sent is not what is equal to received. And we start with essentially computing the entropy of this error and W given what was received. And we have two different expansions for it. Obviously, if we know what was sent and what was received, the uncertainty about the error is 0, so the entropy is 0. Secondly, if we know y, the uncertainty about error in any case is, error is a binary variable, so it's less than or equal to 1. And so then the last thing we have to worry about is this bit down here. And let's just expand that on the next page. So that can be written, again, analogous to what we did in Fano's inequality, as the probability is equal to 0 plus this. Now this quantity here is going to be equal to 0, because when the error is equal to 0, then we know W, right? So it's given W, and we know that the error is equal to 0, that there's no uncertainty about W. So this whole thing is equal to 0. And then this thing is going to be log of the remaining possibility. So like when the error is equal to 1, we say, okay, well, we know it's not that W. It's got to be one of these 2 to the NR minus 1 additional other ones. So that puts a bound on that. And this thing here is just the probability of error. And so that whole thing ends up being less than or equal to probability of error in R. And so we get Fano's inequality from combining the previous page to this page with this page. Actually, well, let me take it back. It's almost Fano's inequality. Forgot about this. So here we can further, again, because taking functions of random variables reduces the entropy. So the code word is a function of the message that's sent. And conditionally or unconditionally, if we take a function of a random variable and the mapping, x of n of w, x of n is a deterministic mapping. So that has only the possibility of reducing the entropy. So we're reducing the entropy and going from here to here. And so what Fano's inequality then is this.
Is that because of the DPI?
Say again?
Is this because of the DPI, the data processing inequality?
I mean, in some sense, you can get this from a data processing inequality. I mean, yeah, I guess that's the way that we showed it. And that's right. So data processing inequality says, but in general, like if you take a function of a random variable, the entropy is going to decrease, and that can come from the data processing inequality. That's right. Okay, so here's the converse. Now, I think we have all of the machinery and tools necessary to prove the converse. So the converse is that, let me just state it again. It says that if the max probability of error goes to 0 as n goes to infinity, then the rate has to be upper bounded by C. So the average probability of 0, the max probability of error going to 0 means that the average probability of error goes to 0. And here's the average probability of error. Right? So the max goes to 0, the average goes to 0. And again, let's also assume that we've got a uniform distribution over the messages. So then here's the actual error. The probability that W is equal to W hat is basically, under the uniform distribution, 1 over m, which is the number of messages, and the sums, so over all 2 to the NR code words being sent, whose error is lambda I. Okay, so this proof is going to be a little bit similar to the 0 error case, except that we're going to use Fano's inequality. So NR is equal to h of W, right, because we're under the uniform distribution. This is the same thing we used in the 0 error case. This is the definition of mutual information. This is using the data processing inequality. Again, exactly the same as the 0 error case. Now here's Fano's inequality, and we're using Fano's inequality to give us this is less than or equal to this. Remember lemma 15.4.1, that famous lemma. So we're using that to get us this is less than or equal to this. So what that means when we divide everything by n is that we haven't assumed 0 error. What we do get is that the rate is less than or equal to the probability of error times the rate plus 1 over n plus c. Now, as n goes to infinity, we know that the probability of error goes to 0, right? Because that's just by assumption. Because if the maximum probability of error goes to 0, the average probability of error goes to 0. That's our assumption. So that this whole term doesn't matter. 1 over n also goes to 0. That term eventually doesn't matter. And so we end up getting that the rate is less than or equal to the capacity. Less than the capacity. So the other thing to note is, like, let's just rearrange this a little bit. So this is sort of rearrange this thing here and put a lower bound on the probability of error. Now this is where this famous plot that I've been warning you about, we're going to derive this from. So the probability of error is less than or equal to, is greater than or equal to 1 minus c over r minus 1 over n over r. Okay. So as n gets big, essentially this second term doesn't matter at all, right? Or sorry, I guess it's the third term. This third term doesn't matter at all. And in such case, when the rate is strictly greater than the capacity, then the error is bounded away from 0, meaning that you always will have a non-zero probability of error, regardless of n. That's a lower bound on the error, saying you got an error, you got a probability of error. Some fraction of what you send is going to be an error. Guaranteed probability. And even for small n, you can say, well, what about when n is really small? Then sort of the probability becomes a little bit meaningless. It's still the case that the probability is bounded away from error, because with small n, we could always essentially group together blocks of small n to make a big N. And because the big N is a lower bound for any code, we can't create a big N code with bunches of blocks of small n. So even though the bound, this particular bound doesn't really apply for small n, which means that the bound could, maybe even go negative. It's just the error can't go below or equal to 0 when the rate is greater than the capacity. So here's the lower bound on the error, and here's where we get this plot. So this is a plot of the log of the probability of error. So it's really like this is the log of this thing. And the x-axis is showing the rate. As the rate increases above the capacity, the error lower bound is going to increase. But when the rate is less than the capacity, the error lower bound is 0, or can be made as close as you want to 0. So the critical point, I mean, this is something, again, it's not that the error is 0 if your rate is less than the capacity, but it's the error as a function of block length going to 0. It's true when the rate is less than capacity, meaning that you can make the block length big and make the error as small as you want. But as soon as the rate is above capacity, you can no longer make the error as small as you want by increasing block length. So that's the critical phase transition that happens at the capacity. Exactly dual to, here's another picture. This is the error exponent. So this is like if we want to, put the error function up in the exponent of e to the negative n e. And it's just looking at the exponent, it's saying, okay, well, the exponent is going to be positive if the rate's less than the capacity, which means that you're going to drive the error down to 0. But the exponent's going to be 0 if the rate's greater than the capacity, meaning that you're not going to drive the error down to 0 as a function of block length.
So what's the error?
Oh, remember, that's the thing that involves like the rate and the mutual information. That's this thing we already saw. It's like the capacity minus the rate, and so it depends on how much it is. But the point is that as long as, remember, it's like the capacity minus 3 epsilon minus the rate. Remember that business. So as long as and then remember 3 epsilon can be made as small as you want. So as long as the rate is, it's basically linear in the difference between the two, capacity and the rate. So as long as that thing is going to be, as long as the rate is strictly less than the capacity, the error is going to drive down to 0 eventually for big enough block length. So there's something else that's kind of interesting. Like we've we've seen this now twice, in the zero error case and then in the actual error case. What we want to do now is in the zero error case, look at if we insist upon the rate being equal to the capacity, what happens to the rate equal to capacity and the error equaling 0? Like, what must be true of a code? So what we're going to do is we're going to drive the same derivation we've done now twice today. But rather than making inequalities, we're going to make everything in equals in order to get nr is equal to nc. And then we're going to see, by making these inequalities inequality, what must the consequences be to show what necessary conditions of a code with such properties are. Properties being the rate is exactly equal to c and the error is equal to 0. So let's see, and then see if that code actually has reasonable properties. So nr is equal to the entropy. So this right away basically says that the code words have to be distinct. You can't have non-distinct code words. Right? This is equal to that according to the definition of the entropy, but because the probability of error is equal to 0, as soon as we know y, we know x. So this whole thing, the whole conditional entropy is equal to 0. Right? And so right now we've already got it in the form of this mutual information, mutual information between these two vectors. And we can write it as the difference of entropies, which we know how to do. And since it's a discrete memoryless channel, we can write it as the sum of these conditional entropies. And furthermore, the other thing that we used to make an inequality in previous derivations was we just said this was upper bound, but we want to make this inequality. And we can make it an inequality by saying that all of the y's are independent. So far our requirements are the code words need to be distinct and all the y's are independent. And that's equal to this mutual information quantity, which is equal to NC. That was the other upper bound. And that's true if we choose this particular source distribution. So we have 3 requirements. Let's just summarize them here. So the 3 conditions for 0 probability and equality in the rate, equality of rate and capacity is that all code words must be distinct. All of the y's are independent. And the distribution on P is capacity achieving. Exactly capacity achieving. So now again, this just says, in some sense, that this is a necessary requirement, not a sufficient requirement. In these kinds of codes, we're not really talking about the world of practical codes. But still, if you were interested in these instances when R is equal to C, this gives you an example. And then in order to actually get one, you need to make additional assumptions, like to talk about a particular code, like a particular DMC, in which case you're actually at the capacity. You know, you need to start dealing with things like dyadic distributions and probabilities of like 2 to the negative k, stuff like that. Okay, so let's now talk a little bit about feedback. So feedback is kind of interesting because you normally think, this is one of the reasons why I like feedback. So I'm X and you guys are Y, right? And I'm communicating to you through a noisy channel. And the noisy channel is expressed by, you know, the room acoustics on the one hand, but it's also expressed by, you know, my imperfect memory and my imperfect ability to explain things as clearly as things could be explained. I mean, every time I explain something, of course, it's going to be a different explanation unless I'm reading. So there's noise, right, in my communications channel to you. So you notice how I attribute my imperfection not to me, but to the channel, right? Not to the source. Right? The source is fine. But the question is, which we want to ask is, okay, so I always ask you for questions because I think I have this belief that if you give me feedback and you ask questions, it helps me to explain things better. And I think it really does. I think when I get questions, the message is imparted in a more efficient way. But let's see if then we can look at feedback in the information theoretic context and see if we can get a better rate. And let me just ask you first, do you think, suppose we send a message, we use a channel, we send it over to you, you get a Y, and then let's say that there's a perfect feedback channel where you can send it back to me and say, hey, this is what I got. And they say, oh, you got this. I'm gonna now adjust my next message and send you another message, and then you send me, hey, this is what I got. So now I can basically choose my messages based both on the history of the messages I sent, but also based on the history of the messages you received.
And this is assuming that you already have perfect information on what the distribution of the channel is.
Yes. Yes, and that's a critical point. So the question is, can I communicate to you at a faster rate? This is the intuitive question to contemplate, given this type of perfect feedback. So me sending to you messages is not perfect, but the feedback I get just so happens. Let's just pretend it's perfect. So in other words, I perfectly understand every question you ask of me,
So
which is not true either. But
the feedback is required to be of that form. You just have, it has to be, you're sending the symbol that you receive.
mm-hmm.
You can't use that to communicate.
Well, I can do anything I want with that symbol. I could use it to construct a new message, a new next message. I mean, I get back exactly what you receive, and I can take any function of that I want. So is that going to improve our rate?
I don't think so. First, the channel is memoryless, right? So the only thing you can do is to repeat and listen to it.
That's anybody else? It's good. What about, do you think that you'd be able to communicate more efficiently? Like maybe computationally efficiently? Is there any benefit potentially? So there's two questions really. Does the rate improve, or does the efficiency or the computational complexity? So I'll since we're running out of time, I'll spill the beans, and as they say. So yes, your intuition is exactly right. The rate doesn't improve. Because in some sense, if you're coding at the capacity already, you already know everything about the channel. And getting feedback it's not going to be surprising to you because you say, well, of course, I mean, look at this. I know this. I know the capacity. I know that there's going to be errors. I've already accounted for these errors in the strategy that I'm coding for you. I'm already achieving. So getting back information is not telling you anything new. But on the other hand, if it can actually significantly help efficiency in coding. Like when you ask me questions, that's useful. So you ask me questions, and I can explain things in a way that's computationally easier to understand based on the feedback I know that everything I'm realizing that you're getting, the information that you're getting from me. That is. And then also, as was mentioned, in the case when it's when it's not memoryless, if suddenly time becomes an issue. And if there are temporal properties that are similar over time, then yes, feedback can help. But let's talk about the memoryless case here. So here's without feedback. So without feedback, basically, every x is sent over to y, and nothing ever happens. Okay. With feedback, on the other hand, we send a message to y, and it's noisy, but y1 gets sent perfectly back to x. And now x2 gets sent to y2, which then when we decide x3, we have all of this stuff, x1 and x2, and we also have y1 and y2. So we have all of this information to send to to generate x3, and so on and so forth. So here's another way of looking at it. So we have this message. It goes over to this noisy channel. The message is basically based on the W and the entire history. So that's how we choose X. And it gets over the channel, and then we get feedback, error-free feedback. Okay. I should have actually done that before I asked you the question. So can this increase the capacity? So that's the question. And no is the answer. So, and we've already talked about the intuition. yes, feedback can make it easier. I think that, remember the binary eraser channel? I didn't mention that. So in the binary eraser channel, if we send something and every once in a while a symbol gets erased, if we get feedback saying, oh, I got the eraser channel, or you can say, what? Sorry, what did you say? It's just really easy to send it again. The decoding and the encoding is really easy. Right. And it can, of course, also help with memory. But we're not going to talk about that right now. This is called a feedback code. It's the 2 to the NRN feedback code, where it's an encoder and a decoder. Now, the encoder in this case gets to use a lot more than what the encoder used before, which is basically uses the W and the whole history of previous messages. And of course, it also can use the previous sent messages too, because you can always use them or just rederive them. And capacity feedback is the capacity of a discrete memory list channel with feedback. So this is just a new capacity. And then the theorem basically says that the capacity, feedback capacity is the same as the regular capacity, which still has the same form. So to prove this, the first way to show it is to show that we're almost done with the slides. I think we can do this without going a little bit too much. But so the feedback capacity is greater than the capacity. Since feedback is a generalization, we can always choose to not use the feedback. And then we can take the entropy, and we're going to essentially compute the Fano bound using W directly rather than X. And this is sort of key because, in some sense, the message really is W, it's not X, not the code words. And we can get this upper bound by Fano. And next we're going to bound this quantity. And this kind of bound is almost the same thing. So we take the mutual information and its definition, and we write it using the chain rule of entropy. And we write it, we add an additional conditioning on X. And this is valid to do because X is a function of both the message and the previous guys. But once we have X, X determines Y. The X is the thing that gets sent. And so all of this other stuff, W and all of the previous Ys are irrelevant to let me write this down just in case this isn't clear. So this is saying that Y of I is independent of Y 1 through I minus 1 and W given X of I. So that allows us to get rid of all of that and write it in this way here. And that we can upper bound again using the additive upper bound of entropy here. And that's the sum of mutual information terms. So, and that's, we know, is less than NC. So we basically done a little bit of manipulation of the mutual information, the entropic quantities, to give us the same upper bound we had before, which was this, interestingly enough. And then we can, so the entropy is less than or equal to the n times the rate, and so we get the same thing. So therefore the rate is less than this. And as n goes to infinity, the rate's less than the capacity. So there's no benefit to feedback. Okay, so that's the end of today's lecture. Are there any questions? We apologize again for all the technical glitches today. I'll try to debug this better for Thursday, but I honestly don't understand what happened. I mean, it normally works. It normally isn't this bad. But also keep your eye out for homework. So any questions at all? No? Okay, I will see you soon.